Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine, just for a moment, the absolute definition of isolation. I want you to close your eyes and just picture a place where the concept of hospitality doesn't even exist.
Not even in the vocabulary.
Not at all. You are standing on a plateau of ice. It's 2 miles high, and the air is so thin it leaves you breathless just standing there. The temperature is hovering somewhere around, I don't know, minus 70, maybe minus 80 degrees Fahrenheit.
And it is dark.
And it's dark, not just nighttime dark, but a heavy, permanent, oppressive darkness that lasts for months on end. You are at the very bottom of the world.
You're painting quite the visceral picture of the South Pole winter. It is, physically speaking, probably the closest a human being can get to being on another planet without actually leaving Earth's orbit.
It definitely feels that way.
Right.
But here's the paradox we're going to be wrestling with today. We're standing in this frozen, silent, basically dead environment, but we aren't looking down at the ice, we're looking up. We're standing next to this massive machine, the South Pole Telescope, or SPT, a 10-meter wide dish that is just staring into the sky, hunting for something.
And it's certainly not hunting for peace and quiet.
Far from it. That telescope shivering in the Antarctic cold, well, okay, the machine is fine, the humans are the ones shivering. It's focused on a region of space that is the polar opposite of where it sits.
Literally the polar opposite.
It's looking 26,000 light years away, directly at the center of our own galaxy, a place defined by heat, violence, chaotic gravity, and just unimaginable radiation.
It's truly a tale of two extremes, isn't it? The coldest place on Earth is our best window for watching the hottest, most violent neighborhood in the Milky Way.
And recently, this telescope saw something. It wasn't just taking pretty pictures to put on a calendar. It caught a series of events, cataclysms, really, that are changing how we understand the survival of stars near a supermassive black hole.
Right.
This is what we're exploring today, and it's all based on these incredible findings published in the Astrophysical Journal.
And it's really a detective story. It's about how we found these, you could call them screaming stars, hiding behind a curtain of interstellar dust, and, why we had to go to the literal end of the world just to hear them.
So let's start with the mission. We aren't just here to say space is cool, though, it obviously is.
It is. That's a given.
We're here to understand a specific discovery. What is the headline here? What did they find?
The headline is that we have opened a new window. For decades, the center of our galaxy was like a locked room. We knew there was a monster inside, this supermassive black hole, Sagittarius A, but the door was blocked by this thick screen of dust.
So you could hear things bumping around in there, but you couldn't see.
Exactly. You could hear some knocking, maybe see a little bit of X-ray light under the door frame, but we couldn't actually see the action. The South Pole Telescope, using a very specific wavelength of light, just kicked the door down.
And what was inside?
What it found inside was a population of stars undergoing these enormous magnetic eruptions. Flares so violent they sort of defy our standard models of solar physics.
Magnetic eruptions. That sounds intense. We're definitely going to unpack that mechanism in detail later. But before we get to the explosions themselves, I really want to understand the tool. We'll talk about the instrument. Why on earth do you build a telescope in Antarctica?
It is a very valid question. Building a sensitive, multi-million-dollar scientific instrument at the South Pole is a logistical nightmare.
I can't even imagine.
You can't just fly in a repair technician from Geek Squad if a fuse blows in the middle of winter. The Winterover crew is stuck there, completely isolated for 6 months. So why do it? Why go through all that trouble?
You mentioned when we were prepping for this that it's all about water, or more specifically, the lack of it.
Precisely. To understand this, we have to talk a little bit about the electromagnetic spectrum. Light comes in many flavors, You have the visible light, which our eyes see.
Red, green, blue, all that.
Exactly. Then you have high-energy stuff like X-rays and gamma rays, and low-energy stuff like radio waves. The South Pole Telescope operates in a very specific, very useful niche called millimeter wavelengths.
Okay, so on the radio dial of the universe, where are we sitting with that?
We're sitting right between infrared light, which you can think of as basically heat radiation, and traditional radio waves. We're talking about frequencies around 90 to 150 gigahertz. Now, here's the problem for astronomers on, well, most of the planet.
Okay.
Water molecules, H2O. They really, really like to absorb light at these specific frequencies.
They eat the signal.
They absolutely devour it. If you tried to use a millimeter wave telescope in, say, Florida, or even a temperate place like France, the humidity in the air would act like a brick wall.
So it's like trying to listen to a concert from outside the stadium, but the walls are 10 feet thick.
That's a great analogy. The water vapor in the atmosphere would absorb all those beautiful signals coming from space before they ever reach your dish. You'd just be looking at noise from the atmosphere itself. It would be like trying to stargaze through a thick, permanent fog bank.
So you need a place where the air isn't just dry, it has to be bone dry.
That's the term, yes. And Antarctica is technically the largest desert on Earth.
Yeah.
Because it is so profoundly cold, the air simply cannot hold moisture. The water freezes out of it.
Oh.
So the column of air directly above the South Pole is incredibly stable and, crucially, incredibly transparent to these specific millimeter waves.
So the extreme cold is actually a feature, not a bug.
For this specific type of astronomy, the cold is the lens. It clears the fog. It provides a level of clarity that is basically unparalleled on the planet's surface. The only better place to put a telescope like this would be in space, which is, as you can imagine, significantly more expensive.
I'm guessing just a little bit.
A little bit, yeah.
Okay, so we've established that we're at the South Pole to escape the water vapor. Now, why do we care so much about millimeter waves? Why go through all this trouble to see in that specific frequency? Why not just use the Hubble or the James Webb Space Telescope?
And that brings us to the curtain. The center of our galaxy is, 26,000 light years away?
Yeah.
Between us and that center lies the main plane of the Milky Way. And it is filled with gas, debris, and vast, vast clouds of interstellar dust.
When you say dust, are we talking about the same stuff that's under my couch, or is this something more exotic?
Chemically, it's not so different. You've got silicates, carbon, little bits of ice. But in space, over those kinds of distances, it acts like a smokescreen.
Okay.
Visible light, the kind that Hubble is famous for seeing, has a very short wavelength. When that short wave of light hits a tiny dust particle, it bounces off or it gets absorbed. It scatters all over the place.
So it can't get through.
It can't.
Yeah.
If you look at the constellation Sagittarius toward the galactic center with your naked eye or a normal telescope, you see these dark patches, these dark rifts. You're not actually seeing the core, you're seeing the shadow of the dust that's blocking the core.
So visible light just hits the wall like it's blocked.
It does. But millimeter waves are different. Their wavelength is much longer. Literally, we measure it in millimeters. And this larger size allows them to sort of slip past the dust particles. They don't interact with the dust in the same way. They punch right through.
I like the analogy of a forest. If I shoot a BB gun into a really dense forest, the BD, which represents the short wavelength of visible light, is going to hit a tree branch or a leaf almost immediately.
Right, it's not getting far.
But if I roll a bowling ball through that same forest...
It's going to keep going. It might get deflected a little, but it's going to push through the underbrush. The millimeter waves are the bowling ball. They navigate the obstacle course of interstellar dust. So while an optical telescope sees a black wall of dust, the SBT sees right into the heart of the galaxy. It lifts the curtain.
Okay, that makes perfect sense. So we have the location Antarctica to avoid water, and we have the wavelength millimeter to avoid dust. Now let's talk about the team and what they're actually looking for. This isn't just a guy with a joystick, right?
Not at all. This is a massive collaboration led by researchers at the University of Illinois Urbana-Champaign and the National Center for Supercomputing Applications. And their methodology here is absolutely crucial. They weren't just taking a long exposure photograph, static image. They were hunting for transients.
Transients? That sounds like people passing through a town. In astronomy, what does that mean?
In the context of the sky, a transient is anything that changes brightness over a relatively short period. Most of the universe, on a human timescale, it's pretty static. The stars you see tonight are the same brightness they were when the pyramids were built, more or less.
They're constant.
But a transient is a dynamic event. It's a flash, a pulse, an explosion, a flare, something that wasn't there yesterday.
So they're looking for movies, not paintings.
That's a perfect way to put it, yes. They're looking for things that go bump in the cosmic night. And to do that, you can't just look once. You have to watch the same spot over and over and over again, comparing images, looking for a change. And that is exactly what the SPT did. It monitored the galactic center over multiple observing seasons, just waiting for a flicker in the millimeter band.
And that waiting paid off. Which brings us to the scene of the crime. Let's go to the destination. We're looking at the galactic center. Can you create a mental image for us? If I could teleport to the neighborhood of Sagittarius A, what is the vibe? What does it feel like?
Crowded and violent are the two words that come to mind immediately. And it's hard to overstate either of them.
Okay.
First, let's talk about the density. In our neighborhood of the galaxy where the sun lives, space is profoundly empty. The nearest star to us, Proxima Centauri, is over 4 light years away.
Which is an enormous distance.
It's a staggering distance.
Yeah.
If the sun were a grapefruit in New York City, the nearest star would be another grapefruit in San Francisco. That's the kind of emptiness we're used to.
Right. A lot of elbow room, spacious, comfortable.
Very. Now, in the galactic center, those grapefruits are all packed into the same stadium. The stellar density is millions of times higher than it is out here. Stars are everywhere you look. And because of the supermassive black hole at the center, they are all moving terrifyingly fast.
And let's talk about the landlord of this stadium. Sagittarius A star. SAG A star, as they call it.
Right. It's the beast in the middle of it all. It has a mass of 4 million solar masses.
4 million times the mass of our sun.
Yes. All of that gravitational pull compressed into a region smaller than the orbit of Mercury. This absolutely dominates the environment. Stars aren't just drifting along in graceful orbits. They're being whipped around at thousands of kilometers per second. It is, and this isn't an exaggeration, a cosmic demolition derby.
And it's not just gravity that's the problem, right? The whole environment is messy.
Extremely messy. You have these powerful, tangled magnetic fields twisting through all the gas and plasma. You have shock waves still propagating from ancient supernovae that went off nearby. You have intense, scorching ultraviolet radiation from massive young stars that formed in that chaotic environment.
So it's a terrible place to be a star.
It's a terrible place to be anything. And on top of all that, you have the tidal forces from the black hole itself.
Tidal forces. We hear that term a lot in science fiction. Captain, the tidal forces are tearing the ship apart. What does that actually mean in a physical sense?
It's a great question because it's a very real and powerful effect. It all comes down to the difference in the strength of gravity across an object. Gravity gets weaker with distance.
Right. The inverse square law.
Exactly. So if you are, say, falling feet first towards a black hole, the gravity pulling on your feet is much, much stronger than the gravity pulling on your head because your feet are closer.
That starts to stretch me.
It stretches you violently. The technical term in extreme cases is spaghettification. Now, apply that to a giant ball of gas like a star. This means the black hole is constantly trying to pull the star into an oval, a football shape. It is squeezing and kneading the star.
Kneading it like dough.
Precisely. And that constant mechanical kneading adds an enormous amount of energy to the star. It churns up its interior, it drives convection currents, it creates turbulence, heat, and friction deep inside the star itself. It's not a peaceful existence.
So you've got this crowded, high-speed, high-gravity, radiation-soaked environment, and it's all hidden behind this thick curtain of dust. And the SPT is just watching it, patiently. This leads us right to the discovery. What did they find in all that chaos?
They found flares. But these weren't just any old standard solar flares. The paper describes them as powerful stellar flares that were so bright they were detectable in the millimeter band from 26,000 light years away.
Okay, let's try and put that in perspective. I mean, our own sun has flares. How do these compare?
It's almost not a fair comparison.
Yeah.
If I lit a match in Los Angeles, you wouldn't see it in New York. The amount of energy you need to release to be visible across half the galaxy it's incomprehensible.
So these are not your garden variety flares?
Not at all. The source material uses a comparison that I think is really effective. They make our sun's most dramatic outbursts look like flickering candles. We're talking about energy releases that are many, many orders of magnitude stronger than anything we experience in our own solar system.
There is a fascinating detail in the report about the images themselves. Something about artifacts in the data. Can you explain that?
Yes, this is a great detail for anyone who's into the tech side of this. The flares were so intense, so concentrated, that they completely saturated the detectors on the telescope's camera.
So too much light.
Way too much. In the digital images, this overload created telltale diffraction spikes and vertical streaks. It's a lot like when you take a picture of the sun or a bright street light at night with your phone camera and you get those lines shooting out from the light source.
Ah, okay, I know exactly what you mean.
It's the same principle. The pixels, the little light buckets in the camera, literally couldn't handle the fire hose of photons. The electrical charge spilled over into the neighboring pixels. So finding these artifacts in the data was basically a smoking gun. It told the astronomers, this isn't just random noise, this is a real point source of incredible power.
And these weren't one-off events. This wasn't just a single lucky shot.
No, and that's a really key part of the study. They found about a dozen of these distinct events over the course of their survey. This implies that whatever is causing this, it's not a once-in-a-billion-year fluke. These stars are flaring regularly. It seems to be a chronic condition of living in that brutal neighborhood.
Okay, so we have stars that are screaming. They're literally blasting out these enormous amounts of energy. The big question is how? What is the physics here? What is the mechanism behind this?
We believe the mechanism is a process called magnetic reconnection.
Okay, I'm going to need the simple explanation on this one. Magnetic reconnection sounds like I'm fixing my Wi-Fi router.
It's a little bit more violent than that, I promise. To understand this, you have to stop thinking of a star as just a solid ball of fire. A star is a fluid. It's made of plasma gas that's so hot the electrons have been ripped away from the atoms.
It's a charged gas.
It's a charged, conducting gas. And because this plasma is constantly moving and churning, it generates incredibly powerful magnetic fields. The star is a giant, spinning fluid magnet.
Okay, that makes sense.
Right. But here's the catch. Because the star is fluid, it doesn't spin like a solid ball. The equator of the star might spin faster than its poles. This is called differential rotation.
So it's twisting itself up.
It's twisting itself up, exactly. The magnetic field lines, which are anchored deep inside the plasma, get dragged around by this uneven spinning. They get stretched and twisted and tangled up over time.
I'm visualizing a big, messy ball of rubber bands.
That is the perfect analogy. Imagine you're holding a bunch of rubber bands and you just keep twisting them. You're storing potential energy in that tangled mess. It gets tighter and tighter. Knots and kinks form. Eventually, the tension becomes too great for the rubber bands to hold. What happens?
Snap.
Snap. The rubber bands break and instantly release all that stored energy. They snap back into a simpler, lower energy shape. In a star, that snap is magnetic reconnection. The tangled magnetic field lines suddenly and violently reconfigure themselves into a simpler arrangement.
And that process releases a ton of energy.
An unbelievable amount of energy. In that instant of reconnection, particles, electrons, protons are accelerated to near the speed of light, and a massive blast of radiation is unleashed across the spectrum.
And that's a solar flare.
That is a solar flare. Now, take that same basic mechanism, but put the star right next to a 4 million solar mass black hole.
Ah, the kneading. The tidal forces.
The kneading. The tidal forces from Sagittarius A are constantly churning the interiors of these stars, twisting those magnetic fields much faster and much, much tighter than a normal isolated star like our sun would ever experience.
So the black hole is essentially winding up the rubber band ball for them, but winding it way tighter than the star could on its own.
You've got it. It's supercharging the magnetic dynamo. So when the snap reconnection happens, it's not just a pop, it's a bomb. It releases a massive pulse of energy, and a significant portion of that energy comes out as millimeter wave radiation.
The source also mentions something called synchrotron radiation. Is that related to this whole process?
It is directly related. Synchrotron radiation is the specific type of light that's produced in this scenario. It's what happens when charged particles, in this case electrons, are moving at relativistic speeds near the speed of light, and they are forced to spiral around a magnetic field line.
Okay.
As they spiral, they scream out energy in the form of electromagnetic waves.
Mm-hmm.
And the signature of that process, the specific color of that light, is very strong in the radio and millimeter parts of the spectrum. The fact that the SPT saw these flares so clearly in millimeter waves is a huge confirmation that this is the physical process at play. It tells us we were dealing with very high-speed particles and very strong magnetic fields.
So the whole chain of events lines up. The black hole distorts the star. That distortion tangles the star's magnetic fields. The fields snap in a reconnection event. Particles get shot out at nearly the speed of light, and we see the resulting flash of synchrotron radiation in Antarctica.
You just summarized a PhD thesis in a single sentence. That is exactly the proposed chain of events.
It's terrifying, but it seems incredibly useful for astronomers. This leads us to the significance of all this. Why is this discovery being called a new window?
It's significant for two main reasons, and they're both really important. First, it's about the method itself. Before this paper, we didn't really know for sure if we could use millimeter waves to effectively hunt for these stellar transients through all that dust.
So this is a proof of concept.
It absolutely is. It validates the tool and the technique. It means we can now start to look at other dust-obscured regions of space, like the dense nurseries, where new stars are born inside thick clouds of gas and dust, and we can watch for flares there too. It gives astronomers a whole new set of eyes.
That's a huge deal.
It is. Imagine she'd had spent your whole life only able to hear. You'd know a lot about the world. But if you suddenly gained the ability to see, your understanding of the world would expand infinitely. That is what millimeter wave astronomy is starting to do for the study of these transient events.
Okay, so that's the first reason. What's the second?
The second reason is what this discovery tells us about the stars themselves. The paper talks about the survivors.
I love that term. It's so evocative.
Isn't it? Because that's what they are. Think about it. We can't see the surfaces of these stars directly. The dust is still too thick for a conventional telescope. But these incredibly powerful flares, they act like probes. The paper compares each outburst to a brief lighthouse flash.
A beacon in the dark.
Precisely. For a brief moment, that flare illuminates the fundamental physics of the star that produced it. By analyzing the light from the flare, its brightness, how it changes over time, its specific frequency, we can deduce things about the star's magnetic field strength, its plasma density, and its overall energetic state.
So you're reading the star's biography by watching its temper tantrums.
That's a fantastic way to put it, yes. We're learning about the normal state of the star by studying it during its most extreme moments.
So without the flare, the star is effectively invisible. The violence is the only reason we know it's there and what it's like.
And that is the profound irony at the heart of this discovery. If these stars were peaceful, stable, and quiet, like our sun, they would be completely lost in the gloom of the galactic center. We would never be able to detect them through the dust. It is their violent struggle, their kicking and screaming against the influence of the black hole that announces their existence to the rest of the universe.
That's almost philosophical. It's like, I flare, therefore I am.
In the galactic center, yes. It seems that survival is noisy, and it forces us to reconsider what we mean by a habitable or stable environment for a star. These stars are proving that existence is possible even when you're living in the teeth of a monster.
So what does this discovery mean for the big picture? Let's talk about the implications. We're trying to build a complete model of our galaxy, right? How does this new information slot into that?
It slots in by helping us understand the ecology of galactic cores. For a long time, we sort of thought of the center as just a graveyard, a place where things go to get eaten by the black hole, a final destination.
Right, the end of the line.
But this research, and others like it, shows that it's a dynamic, active ecosystem. Stars are surviving there. They are interacting, they are evolving, and they are flaring. It's a habitat, just a very, very extreme one. Understanding which types of stars can survive there and how they do it is a huge piece of the puzzle of galactic evolution.
And does this help us understand other galaxies too?
Oh, absolutely. That's one of the main goals. Nearly every large galaxy, we think, has a supermassive black hole at its center. We can't see the individual stars in the centers of other galaxies with this level of detail. They're just too far away. So Sagittarius A is our local laboratory.
It's our petri dish.
It is our petri dish. If we can understand the exotic physics of stars surviving here in our own backyard, we can then apply those models to understand what's happening in things like quasars and other active galactic nuclei that we see lighting up the distant universe.
So looking forward, what are the next steps? What happens now?
More data. Always more data. The SPT is continuing its survey, and similar telescopes are also watching. We want to build up a much larger catalog of these events. We want to know, do these flares have a pattern? Are they periodic?
You mean like, does a certain star flare every 40 days, or is it completely random?
Exactly. If we found a periodicity, that would tell us something profound about the star's orbit or its internal magnetic cycle. And a huge question is, are there different types of stars involved?
Right. Is it only the massive young blue stars that are doing this? Or can old, smaller red dwarfs flare like this too when they're in that environment?
We need a census. We need to figure out the demographics of this flaring population. And the other big step forward is what's often called multi-messenger astronomy.
That's the big buzzword in the field right now. It's about connecting the dots between different kinds of observations.
It is. The dream scenario is this. The SPT in Antarctica spots a flare in millimeter waves. It instantly and automatically sends an alert to, say, the Chandra X-ray Observatory in orbit and maybe some radio telescopes on the ground. The message says, hey, look at coordinate X right now. Something is happening.
So you get all these different instruments looking at the same event at the same time.
At the same time. And if we can catch a flare in millimeter waves and X-rays and radio waves simultaneously, we get a complete 3D picture of the physics. We see the particle acceleration from the millimeter waves and the extreme thermal heating of the plasma from the X-rays. It would be a complete blueprint of the explosion.
That's the dream scenario, total wavelength coverage.
That is where the entire field is heading. Real-time coordination between telescopes on the ice, on mountains, and in space. It requires this incredible level of global and, I guess, orbital cooperation.
It really highlights how interconnected modern science has become. I mean, you have people sleeping in parkas at the South Pole who can trigger an observation on a multi-billion-dollar satellite controlled by a team in Cambridge, Massachusetts.
All to catch a flicker from a star whose light has been traveling for 26,000 years. A star that might not even exist anymore.
Well, 26,000 years ago, it existed with a vengeance.
That's a fair point. We are, in a very real sense, watching history unfold.
So let's try to wrap this all up. We've taken this incredible journey from the frozen plateau of Antarctica to the fiery core of the Milky Way. We've learned about bone-dry air, millimeter windows, and this violent process of magnetic reconnection.
And we've seen that the universe is far more dynamic and violent than our quiet night sky might suggest. We've learned that what looks like empty space to our eyes is actually teeming with this high-energy drama.
I want to leave everyone with that final thought you brought up about the lighthouse. I think it's the most powerful and sticky idea from this whole conversation.
It really is a powerful metaphor.
We usually equate destruction with loss. We think of explosions and cataclysms as endings. But in this specific case, in the darkest, dustiest, most dangerous part of our entire galaxy, it is the violence itself that allows us to see. The destruction is what creates the signal.
Without those flares, the stars would just be invisible ghosts lost behind the curtain.
Exactly. If those stars were peaceful and quiet, they'd be hidden from us forever. It's their constant struggle, their kicking and screaming against the black hole's gravity that announces their existence across thousands of light years.
It really does suggest that in the cosmos, discovery and destruction are often two sides of the same coin. We learn the most about the universe when things are at their most extreme, when they're breaking.
So the next time you're out on a clear night and you look up at the Milky Way, that faint, cloudy strip across the sky, just remember what's really happening in the galactic downtown district. It's not just a soft glow. It's a demolition derby. And there are eyes in the ice at the bottom of the world watching it all happen.
And finding more all the time. Keep watching.